that again is only taught in BC, but it will focus on a special type of definite integral for us to kind of explore and deal with. So to kind of start off with today's notes, I was just going to show some examples of like, here's some problems that would involve an improper integral or be called an improper integral, and then kind of show you how we solve them. I will say the way we solve this, the steps and the notation that we show is important when it comes to answering questions on the AP exam. So not only will we need to know how to do it, but like when to recognize it, and then also kind of showing the notation and the steps clearly. So some problems that would be considered to be improper integrals would be examples of these four. So when we're looking at these four examples, I think some of them you can look at and you can definitely imagine why they would be considered to be improper integrals. Some of them I think are a little bit less obvious that they're improper integrals. This first one, so one thing we notice about improper integrals is that they all are definite integrals. There's not going to be like a plus c. They all have numbers or at least values on that integral sign. These first two are considered improper integrals because we are integrating over an infinitely large region. So like that first one, we're integrating from 0 to infinity. That second one, we are integrating from negative infinity to 1. Those are going to be the ones that are obviously improper integrals. These ones at the bottom are going to be less obvious that they are going to be improper integrals. These bottom two are considered improper integrals because we are integrating over a vertical asymptote. So remember when we first talked about that first fundamental theorem of calculus, that told us how we evaluate integrals. Like we first find the antiderivative and then we plug in the top number minus the bottom number. Well, the first fundamental theorem of calculus only works if f is continuous. So these are going to be examples where we technically aren't going to be using the first fundamental theorem of calculus because these functions are not continuous over that interval. And what I mean by that, this first one we can see in the denominator we have x minus 1. So we know that x itself cannot be equal to 1. But if you're looking at the region that you're integrating over, we're integrating this one over the region from 1 to 10. So that 1 is providing kind of an issue in this problem. This other one, why we have an issue, if I rewrite it so that dx is off to the side, I think it's a little bit more clear. So I have 1 over x squared dx. This one also has a vertical asymptote in it. X cannot be equal to 0. We know that we can't divide by 0. But 0 is included within the interval from -1 to 2. So there's some issues in this one where it's not continuous on that region. So we would consider those to be improper integrals. To give you a formal definition of an improper integral, we're going to say that the integral from a to b of f of x is an improper integral if, and again, all improper integrals are going to be definite integrals. There's not going to be a plus c or anything like that. And what we're going to say makes an improper integral improper is a is infinite, meaning it could be a negative infinity or a positive infinity, and or b is infinite, and again it could be a negative infinity or a positive infinity, and or f of x has a vertical asymptote on that interval from a to b, including a to b. So it could just have one infinity sign. It could have two infinity signs on it. It could have one vertical asymptote within the region, or it could have more than one vertical asymptote in the region. But that's what we're going to consider to be an improper integral. So for the rest of the notes, I really just have example after example to kind of so you can see how to do it, the notation that we can use, and then just how we answer it. Before we answer it, though, there are going to be different things we're going to look for in terms of our answer. And I'm going to introduce two words, converging and diverging. we actually spend a whole lot of time talking about this idea of converging and diverging in that infamous series unit you hear so much about in BC. We kind of introduced the topic of converging and diverging with improper integrals. We are going to say that the integral converges if the integral value is a real number. Your answer to something will be converged will be something like the integral converges to, and then like some number. That's basically what we've been looking at before with definite integrals. We know we find like the antiderivative, plug in the top minus the bottom. It gives us a number, so in many ways those are converging to that number. Diverging is kind of what we use, like for limits we say D and E, for like algebra things we say undefined. We're going to describe integrals as diverging if they do not have a real numbered answer. So we're going to say that an integral is divergent if the integral value is not a real number. The way we're going to answer these questions, we're just going to say the integral diverges. And when I say that an integral is not a real number, we're basically going to see that a lot of these cases are going to be ones where the integral would be approaching like an infinity or a negative infinity, or is like an undefined. So something that's just not a real number, whether it's an undefined or approaching an infinity, that's what we're going to say as divergent. Before we look at any of the examples, any questions on any of the vocab I've gone over so far? All right, so let's just go ahead and look at a few examples. I have 6. We probably will just get through 5 of them today. So here's a pretty simple one that we're going to look at. It has an infinite upper limit. So like automatically when we see this, we know that we have an improper integral because if I can change it, my eraser's not working. 1 second, guys, my OneNote eraser's not changing. And we're back. There we go. This one we can see, as I was saying, is kind of obviously an improper integral because we do see that there is an infinite sign, infinity, on one side of this integral. So when we're looking at this problem, we know that it's going to be an improper integral. We can't solve this like we normally would for like a regular definite integral. Like we can't use the first fundamental theorem of calculus because we are approaching a region without bound. So the first step that you're going to do is you still want to figure out what that antiderivative is. So this is like a pretty simple u sub, probably wouldn't need to show the steps for it, but if u is negative x, u prime would be -1. So the antiderivative of this one, we would have a negative e to the negative x. And here's where I do want to talk about some of the notation that is going to be important that we are going to have to show kind of clearly. We are going to want to clearly define the antiderivative. And we're going to do that by using like the capital F of x notation is equal to the antiderivative. So if I'm looking at this problem, if I can spell derivative correctly, the antiderivative for this one is this negative e to the negative x. I'm going to clearly label that as the antiderivative by calling it capital F of x is equal to negative e to the negative x. The reason why we want to do this is we know normally when we find an antiderivative for a definite integral, like we'd have the antiderivative and we use that vertical bar to show that we need to plug some numbers into it. If you show this on the AP exam, or if you show that on any of my assessments, you're going to lose points. Like infinity is not a number, so we can't use that notation when evaluating this type of integral. So we're first going to kind of clearly show what the antiderivative is. And then once we have the antiderivative, we're actually going to split this up into two limits. And you might be thinking, why are limits showing up when we're taking an antiderivative, when you're evaluating an integral? The reason why we want limits is, again, infinity is not really a number. It's something that these values are approaching. The way that we deal and kind of reconcile with infinity in calculus is going to be limits. Like I can't plug in infinity, but I can take the limit as x goes to infinity to kind of figure out what this might be approaching. So we're going to take the limit, and again, we're still going to follow the first fundamental theorem of calculus a little bit. So I'm going to have the limit for the top value of the antiderivative, and then the limit of the bottom value of that antiderivative. Now this is a limit, so it might be useful to you to rewrite your antiderivative so it's a little bit easier to find that limit. Like for example, if I have a negative exponent, I would probably rewrite this as -1 over e to the x. And then it becomes a pretty easy limit to take. So if x is going towards infinity, we have e to the x in the denominator. If your denominator is getting really, really, really large, then that fraction is going to go to 0. This other limit is a little bit easier to evaluate. I can go ahead and plug in the 0 directly with some direct substitution. E to the 0th is 1, which is going to give me -1. And then it's not the first fundamental theorem of calculus, but we can kind of still follow the idea behind it. We're still going to do the top minus the bottom. The top limit gave us a 0 minus the bottom number, which gave us a -1. So this integral is equal to -1. A way of saying this is we're going to say that it converges to +1. I think it's a -1 there, but it converges to +1. Those are the steps that you would have to show. So again, clearly showing the antiderivative, showing two limits, and then showing where you do the top limit minus the bottom limit, and then what that would be equal to. Questions on those steps or that problem?
What does it mean to converge to 1? Like, what is that?
We are literally saying that this integral from 0 to infinity is equal to 1.
Equal to 1. Okay.
And we're using converges because some weird things are happening, and I don't want to go off on like too much of a tangent, but like what's happening, and we'll spend a lot of time dealing with this with that series unit. We just haven't gotten there quite yet with like some of the other stuff we need to know. But this graph, e to the -x, like that's an exponential function that's been reflected over the y-axis. So it looks something like this. It has that horizontal asymptote that's always getting closer and closer to the x-axis. And we know that when we see a definite integral, this does represent the area, and we have kind of some weird things going on here. So we are literally finding the area from 0 towards infinity, which I know your brain and your gut wants to tell you, like, well, if I'm going out towards infinity, clearly the area is also going to have to be infinity. But what's happening is this graph is getting like exceedingly close to the x-axis, that you're just adding like a smaller and a smaller and a smaller value each time, that it ends up being like in kind of some ways like this repeating decimal, where like the actual area isn't rounded to 1, the actual area is 1, not to like confuse you or anything, but we have like this infinitely large region that has a finite area. So, and that's why we're kind of using the word converging instead of just the area is 1, even though the area is mathematically 1.
One more thing to
say it again.
Yeah, one more thing to add. If there was like a 5e -x, would that change the whole thing?
If that was a 5e to the -x, your antiderivative would be -5e to the x. So it would have a different area, but it would still converge because that limit would still be 0.
Okay, so you would do it similarly. Okay.
You do it the same way.
Thank you.
Try this one for me. This one, the limit, I think is a little bit hard to evaluate. I'm going to be honest and kind of say heads up on that. But I think the setup and find the antiderivative is pretty simple. Again, clearly we know this is an improper one because of that negative infinity. So like mathematically, we're finding like the area from negative infinity to 1, which is a kind of weird concept to do, but we can use this idea of improper integrals to evaluate it. So go ahead and at least do the setup for that one. I'll help you with the limit of this one because it is a little bit tricky, I think. So again, this one we kind of want to treat it like we've done before. We want to find the antiderivative or the integral of this. Looking at your exponents, the difference of the degrees is more than 1, so it's inverse trig. No square root sign and a plus, so we know this is the arctangent, and there's no like worrying about the a value or u sub. Like the integral of this is literally the arctangent of x. So that is your antiderivative. Again, you don't ever, ever, ever want to show something like this on a sheet of paper. Because again, negative infinity is not really a number, so that type of notation doesn't work. That's why we need to do the limit notation. Still going to do top minus the bottom, so when I do the limit as x goes to 1 of that antiderivative, well, the arctangent of 1, asking yourself when is tangent equal to 1? Tangent is equal to 1 at pi over 4. Under the domain restrictions for arctangent. The one that I think is tricky is thinking about the limit as x goes to infinity of arctangent of x. Maybe you get it better than students have in the past, but here's how I kind of think about it in my head. And again, this is kind of just going on in my head and not really being written down as work. But if I am trying to take the limit as x goes to a negative infinity of arctangent, like you can't really do direct substitution because obviously negative infinity is not a number. So in my head, I might just think about, well, what is the arctangent of a super big negative number? And I think dealing with the inverse trig can be a little bit trickier. So you might think about it as what the tangent of something is a really, really, really big number. And you're like, well, how am I going to figure that out? Like, I know the unit circle, but like clearly there's not a negative infinity on the unit circle. But again, if I think about arctangent, arctangent is in the first or the fourth quadrant, and it is bounded between negative pi over 2 and pi over 2. So when I'm thinking about arctangent and tangent, like this negative infinity, how I'm thinking about this in my head is I know tangent is opposite over adjacent. So this is like a negative infinity over like a 1, if you will. So it's kind of like you have a super, 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 super big opposite side and a really, really tiny adjacent side. And if you can kind of imagine if that opposite side of that triangle really did approach infinity, well, then that angle you're approaching would be negative pi over 2. And that's one way to think about it. I think another way to think about it, you would have to just know what the graph of arctangent looks like. Not sure how many of you know the graph of arctangent, because I know I didn't spend a lot of time graphing inverse trig last year. But arctangent is like the tangent formula, but just tangent graph, but just on its side. And arctangent looks like this. And I think that's also pretty easy to do if you know what the arctangent graph looks like. As arctangent approaches negative infinity, then clearly it's bounded between negative pi over 2 and pi over 2, and that's where that pi over 2 is coming from. Looking at both of these are both real numbers. We didn't get like a D and E or an undefined. So since both of those are numbers, we have the top one minus the bottom one, which of course we can write as pi over 4 plus pi over 2. This would be an integral that converges because we do get a real number there. And again, visually what's happening, I know this is the equation of a bell curve of sorts, just because I've been doing math for a long time. And literally what we're saying is that the area from 1 all the way back on this bell curve that goes on forever is equal to pi over 4 plus that pi over 2. Questions on that problem?
Would it be wrong if we just added it up and put down 3 pi over 4?
No, it would not be wrong. All right, let's try some other ones. Try this one on your own for me. Still same process. I have infinity on the upper and lower limit of integration. Do want to make sure you at least get started on the right track. Remember the rule we have for integrating exponentials. We want to make sure we pull it out of the denominator to get the u sub to work out correctly. But go ahead and try that one on your own. Again, if you get a real number for both of your limits, then it converges. If you get like a d and e for even one of your limits, then that whole integral is going to diverge. But go ahead and try that one, and then we're going to look at a few examples with vertical asymptotes. So looking at this one, again, any integration method that we've learned can show up all the way up to integration by parts is what we did yesterday. This one we're kind of saved. We don't need to worry about integration by parts because the u substitution did work out correctly. If this had been like x over e to the x, then we would have had to do some integration by parts. But after doing the u substitution, I have that the antiderivative is -1/2 e to the negative x squared. Could leave it like that. I know I'm doing a limit, so I'm going to get rid of that negative exponent and just rewrite it as -1 over 2e to the x squared. Doing your limit, x is going towards infinity and negative infinity, but it doesn't really matter because that is e to the x squared, so it's going to be positive. Either way, that denominator for both of them is getting exceedingly large, where the numerator is remaining at a -1. Both of these limits are approaching 0. Those are real numbers. Top minus the bottom, the answer to this integral, it is converging to 0. Visually, again, you don't need the graph to kind of do this, but I think it's nice to see why it is that. I know that this equation looks something like this. So if you are integrating it from negative infinity to positive infinity, mine should be a little bit more symmetrical, but basically it's the same area, top and the bottom. The net area would end up being 0. So that's why that one ends up being 0. Questions on that one? All right, for the sake of time, I am going to do 4 on Monday, but I did want to do at least example number 5 today, and we'll do number 6 on Monday as well. But I do want to do example 5 with an interior vertical asymptote. These are the ones that students are most likely to mess up. Because if you're not careful, like even for most of you, even for a lot of teachers, if I show them this question, like they would just jump right in and be like, all right, I'm going to go ahead and rewrite this problem. That's going to be x to the negative 2 dx, pretty easy antiderivative, add 1, divide by the new exponent, plug in the top and the bottom, and then answer it from there. If you do that for this problem, you would actually get the wrong answer because there's an issue with this integral. And the issue with this integral is that x cannot be equal to 0. So you're integrating over a vertical asymptote because we're integrating it from negative 1 to 2. And 0 is between negative 1 to 2. To be clear, if I was integrating from 1 to 2, it wouldn't be an issue because 0 would be outside of that interval. But since 0 is inside that interval, we're not dealing with like an infinity right now, but we do want to somehow take care of that 0. And the way that we take care of that 0 is we're going to split up the integral at the vertical asymptote. So I'm going to have 1 over x squared dx. That first integral is going from negative 1 to 0. And I'm going to add to that the integral from 0 to 2 of the same thing with respect to dx. So again, the issue was that x cannot be 0, so I split up this integral so that 0 is kind of like the dividing point between it. And then from there, I can go ahead and just treat it like an improper integral. We do have 2 integrals here that we're going to have to deal with. They all had the same antiderivative. So the antiderivative of this is that negative x to the negative 1, or negative 1 over x if I rewrite it as a fraction. We are, though, going to have to do 4 limits for this one, which is kind of obnoxious, but we have 2 limits each. They're both improper, so we need to do the top and bottom limit for each of them. So like this first one, we're going to have the limit as x goes to 0 of the antiderivative. We will have the limit as x goes to negative 1 of the antiderivative. And then for that second integral, its top one is 2, not 0. And then its bottom limit, one that we'd have already done, I'm going to write it up here so we can see it, would be 0. So evaluating these, let's just go ahead and do the first one first. So I have the limit as x goes to 0. Well, this antiderivative was negative 1 over x. Well, if x is going to 0, we have negative 1 over 0. Negative 1 over 0 is going to give us undefined, so we know that this limit is d and e. D and E is clearly not a real number, so is it worth our time to go ahead and evaluate the remaining integrals? And the answer is no. Like we already know that this is not a real answer. So who cares about those? Not a real number here. So what would we say about this integral, the original integral that we were given, diverges? And I am going to use that phrase diverges. We're not going to describe that an integral is d and e. We're not going to say that an integral is undefined. We're going to be specific and use that and say that the integral diverges. Questions on that problem? All right, so I'm going to stop there for today. I could probably do one more problem, but I don't feel like rushing it and then running out of time. So we'll finish up example 4 and example 6 on Monday. Example 4 is just one where the vertical asymptote is the first limit of integration, but we'll still break it up in just 2 limits. And I did one that just has a little bit of a tougher limit for us to evaluate. Also a fun one that would use integration by parts. The homework I'm assigning, so it's on the calendar, share with you in OneNote. So hopefully you're mostly done with homework 1, or you've at least started it. Today I'm going to be assigning the improper integrals one. It is a bunch of kind of random numbers. The textbook doesn't teach improper integrals as its own kind of topic. So I had to go and find some questions that's kind of like a random list for you to practice with. So when we regroup and come back to school after the weekend, or I guess virtually, we'll finish up those notes with improper integrals. And then on top of that, we'll go ahead and begin this idea of the second fundamental theorem of calculus, comparing it to the first fundamental theorem of calculus. So with that being said, I'm done with the online portion of class. If you're good to go, then I will see you on Monday. Enjoy your weekend.